Good evening to colleagues in the US and good morning to those from Asia. Welcome to our webinar on China's coal mine methane emissions, spatial and temporal trends, uncertainties, and data dashboard. My name is Jiang Lin. I'm a staff scientist at the Lawrence Berkeley National Lab and a research professor at UC Berkeley. Today, my colleague and I will share with you our latest research on coal mine methane emissions in China. After our presentation, we'll have a moderated discussion by three distinguished panelists. Next slide. So as you all know, methane is the second largest greenhouse gas after CO2. It's a highly potent and short-lived climate pollutant. Its emission have contributed to about 30% of current warming. According to the United Nations, reducing methane emission can significantly reduce near-term climate impact by avoiding 0.3 degrees Celsius in temperature rise. That's almost 3 times as much impact on temperature increase as that of reducing CO2 emissions. China is world's largest methane emitter and has stepped up its policy actions in recent years to control its methane emissions that include the release of the National Methane Action Plan last year and issuing a joint Sunlight statement with the US, committing to issue enhanced national determined contributions, including all greenhouse gases. There are also other sectoral policy at work, including a newly proposed revision of coal mine methane standard, which will drop the threshold for release from 30% to 8%. And it also is developing a protocol for its voluntary carbon credit program to incentivize coal mine methane utilization. Next slide. In China, the largest source of methane emission is from coal mining activities. In comparison, the oil and gas sector is the largest source of emission in the US. Next slide. There is a growing body of scholarly research on coal mine methane emissions in China, including, for example, Liu et al. That has constructed a detailed coal mine database to estimate China's coal mine methane emission during 2011 to 2019, including those emissions from abandoned coal mines. Shen et al. Developed a high-resolution methane emission inventory, yet there are still significant gaps in our understanding of what influence emissions at the individual coal mine and the large uncertainties associated with the methane emission estimates. Next slide. So to address these gaps, our team aims to answer the following questions. What determines the variation in coal mine methane emissions? Is it geographic location, the size of the coal mine, or depth of the coal mine, or ownership of the coal mine, or the methane gas level? And how do we improve geographic resolution of coal mine methane estimates and their uncertainties? I'm going to turn over to Bobing to address the result on the first question.
Thanks, John. Let me first give an overview of the data sets we used in this analysis. So the core data set we're going to use to estimate the emission factors would be this National Coal Mine Methane Level Identification Database in 2011. It's published by the State Administration of Coal Mine Safety, and it covers virtually all coal mines in China, and it has information about gas levels, about location, and then ownerships for this kind of coal mines. It's also used in previous papers. For example, this one and all applied energy paper. These 3 graphs are directly sourced from their paper. As we can see from panel A, it shows the ownership of these enterprises. This large yellow shows these are like small township coal mines. And then we have a few bluish locally state-owned coal mines, and then some large state-owned coal mines. For panel B, we have the gas level identification for each of the coal mines in this sample. We have a lot of low gas coal mines, intermittent with some of the high gas and outburst mines. There are patterns maybe I want to point out. For example, we have quite a lot of high gas and outburst mines in Guizhou and in Shanxi. While in Inner Mongolia, mostly the coal mines are of low gas. They have lower emission factors. And in panel C, we also have the maximum mining depth for each of these coal mines. In the previous literature, there are discussions about mining depth being an important determinant of emission factors for coal mines, and we're going to try to shed light on that here. Yeah. So previous studies have recognized the importance of mining depth in estimating coal mine methane emissions. For example, this Collard et al. Paper in Journal of Cleaner Production have this plot for different types of coals. We have the anthracite and bituminous and subbituminous coals. They all have different relationships with respect to emission factors and mining depth. This is largely arise from a theoretical model developed over a century ago, trying to shed light on the coal mine depth and the emission factor of that coal. So the intuition is quite simple. As we go deeper into the earth, the pressure would grow larger, so that the gas content in the coal sample would be larger as well. Next, please. So in this paper, this first question we're trying to answer is, given the observed emission factors, we want to see what are the big determinants of the emission factor. So as John have mentioned, we have these sort of variables. We have the gas level identification for that coal mine. This is purely based on the emission factor. And then we also have the location, which is basically the province of location for that coal mine. And then we also have the ownership structure, whether it's state-owned or it's township-owned. We also have mine depth for that coal mine. We have production capacity, like how many coals does the coal mine produce every year. So what we're going to do is we're going to regress the emission factor on all these covariates, and to see statistically which factor would influence the emission factor more significantly. So the results are shown in the table below. So for this regression, these coefficients, these betas, would indicate whether this corresponding factor is a significantly contribute to the emission factor. So here, for example, in the table in row 1, we have the first specification. What we're going to do is we're basically going to plug in each one of those variables one at a time in the regression, and to see whether it's significant or not. So in row 1, we only input the province and gas level information. So these ticks would indicate that these information are significant with respect to emission factors. And then in row 2 to row 5, we will stepwise input the ownership structure and the coal mine depth, and also production capacity within these regression specifications. And as we as we reported here, none of these other factors significantly influences the emission factors we observe. So this sort of answered the first question of how these variables would affect our observed emission factor. Importantly, we do not find any significant relationship between coal mining depth and emission factors. Next, please. So with that equation in mind, we can actually estimate the emission factors for individual coal mines. So this is actually based on the newly collected data from 2022 and 2023. So here we're only use the Shanxi province and Guizhou province as examples. For Shanxi province, we have around half of the coal mines operating right now in Shanxi, and as we can see, there are quite a lot of low gas mines, and then each dot on this graph would indicate the actual methane emissions from that coal mine, and then so it's basically a product of the production times the emission factor we estimated from the previous specification. And then on the right, we also have the methane emissions for individual coal mines in Guizhou province. As we can see here, Guizhou has a lot of outburst mines. That's why you see a lot of red dot here. So the emissions from the coal mines in Guizhou are on average larger than those in Shanxi province. So with that, I'm going to turn it over to Jie, who will talk about provincial estimations.
So we estimate the provincial emission factor based on the production weighted average. The production weighted average can avoid the bias by some small coal mines which may have a lower production but have extremely large emission factor. We use the bootstrap to repeat calculating the average emission factor, and the bootstrap results theoretically follow normal distribution. And confident interval of 95% confident interval we see as emission factor uncertainty we use to estimate national and the provincial emission uncertainties. So first, the provincial emission factor for each gas level from low gas, high gas, and outbursts, we can clearly see it has a very distinct geographic distribution. Generally, it has a much higher value in the southwest of China, but a lower value in the north and the northwest regions. The emission factor from low gas, we see the color bar, it's typically lower than 8 cubic meter per ton, which is significantly lower than those from the high gas and the outburst mines. As our statistics show, the table showed before, the ownership structure and the mine depths have less impact on the emission factor compared to these geographic distribution or gas level. We also compared the emission factor from 2011 to 2023. In 2023, we only can find 450 mines in 8 provinces in China, but the distribution looks pretty close. The median value of the emission factor in each gas level are consistent for the 2 years. That provides us some confidence to use the emission factor estimate the emissions of coal mine in China from 2000 to 2023. So this is our estimation. In addition to the emission factor and the production, we also consider the national level of abundant coal mine emissions. And we also consider the national utilization amount. So the shaded area in this plot represents the uncertainty we estimate using the 95% confident interval. And our national uncertainty of coal mine emission is generally about 17% for each year, which is much lower than the previous estimate of more than 50%. And our estimation generally agree with most inventories and the previous study published. The China coal mine methane emission increased very fast with coal mine production growth since 2000 and reached a peak value of about 21 teragram in 2013, in year 2013. So after 2012, the coal mine production in China experienced a decline, but it rebounded in 2017. However, if we see this plot after 2007, the emissions are not responding immediately increase. For example, if we pick 2 points here, 2012 and 2020, so both years the production is about 4,000 million ton. However, the emission in 2012 is about 21 teragram, and in 2020 there's only 17 teragram. And this reduction in coal mine methane emission can attribute to one is the regional production shift, and the other one is the utilization technology improved. So we'll talk about this later in more details. So since 2020, total CMM emission estimates in China start increase again here because of the coal production, national coal production keep increasing and exceeded the 4,000 million ton. So based on the latest year, our production data in 2023, our estimated CMM emission in each province generally have uncertainty about 10 to 25%. And the Shanxi is still the largest CMM emission province in China. It has about the 9 teragram in 2023, and Guizhou is the second one. Guizhou doesn't have a lot of the coal production is not like top 3, but due to the large emission factor, the emission is much higher than other provinces. So it's followed by Shanxi, Inner Mongolia, and the Xinjiang. Inner Mongolia and the Xinjiang, they are the top, the second one and the third one in the coal production in China in 2023. But due to the lower emission factor, their emissions are much lower than Guizhou or Shanxi province. So as we see before, we compared the 2012 and the 2020. The coal production both years are about the same, 4,000 million ton. But if we see the distribution, in southwest region, the coal production are reduced from 12 to 21. But if we see the coal production in Inner Mongolia and Xinjiang here, they are significantly increased. So we did some calculation compared with the production in 2012. By 2023, the north and the northwest regions, like these 5 regions, have increased the coal production by over 800 million ton, but the CMM emission only increased by 1.2 teragram. However, in the southwest area, like this orange line, after 2012, there's a decline of coal production in these regions. The total production in southwest have been reduced by 180 million ton. But this 180 million ton, it has a reduction of CMM emission by over 2.7 teragram. So from this figure, we can see now the national CMM emission is not increased, it's not so much higher like 2012, but our production is already much exceeded the 2012 production. And as we see, the Shanxi province is still the largest CMM emission in China. Our estimated emission, time series emission generally agree with the bottom-up estimation from previous study, and also agree well with the top-down analysis from Peng et al. On 2023 paper. And our uncertainty successfully covered this discrepancy of the previous study. So make a conclusion about our study. The emission factor in China, the CMM emission factor in China show a very distinct geographic patterns, higher in southwest region and lower in north and northwest region. The methane gas levels is very significant to predict or influence the CMM emission. Well, the mine depths and ownership structures, that is not very important. The provincial and the national CMM emissions, along with their uncertainties in this study, we constrain the uncertainties about 17%. And our estimated production weighted average emission factor, and with a calculated emissions estimate CMM national emissions show good agreements with other inventories or previous study. So finally, the total CMM didn't respond or increase immediately after the rebound in coal production, national coal production, mostly due to the shift in production from southwest regions to northwest region, from higher emission factor regions to lower emission factor regions. And a small extent is also because we have increased the CMM utilization in nationwide. So our study provides some insight into the CMM emissions and highlight the significant trends and the policy impacts. So in the future, we would like to compare our bottom-up mine-specific emission, like those points shown before. We would like to compare with the top-down analysis, like from the inverse modeling of the satellite. And eventually, our objective is to develop a comprehensive and a mine-specific emission factor database by incorporating the satellite analysis. So finally, our colleague Bobin has created a dashboard to show our results online and also display our database. So Bobin, can you take over to show the dashboard?
Okay, can you see my screen?
Yes.
Okay, so now in the interest of time, I'm going to give a quick overview of the data dashboard. To access that, you can Google LBNL, Energy Markets and Policy Tools and Data. So it's going to be the first Chinese coal mine methane dashboard. Within this dashboard, we are going to have 4 subplots. Each will have a notes that have more detailed information in case it's not very clear from the graph. So the subplot A would have the coal production and methane emissions for entire China at the province level. So for example, if I hover on Shanxi province, it's going to show that the coal production in 2023 is 1.3 billion tons. And then the estimated methane emission in 2023 is around 9 teragram. And then there's also going to be these average emission factors for each for mines at each gas level. This is going to be based in the 2011 data. So ideally, if you have the location of the coal mine and then you have the gas level of the coal mine, you could use this dashboard to calculate the total methane emissions from that specific coal mine. In subplot B, we also have the coal production and methane emissions for each province or China nationally here over the time period 2000 and 2023. So here it's showing the total methane emission for entire China from this solid red line here. And then these gray solid lines are the uncertainty range for the methane emission estimates. These dotted black line is the coal production. This is based off the data from National Bureau of Statistics. So here, if I click on the Shanxi province in the first plot, everything is going to sync to show, for example, here the methane emissions in Shanxi. And then in the third plot, we're going to see the specific coal mines in Shanxi. And this is based on the 2019 data on the coal mine capacities. We have the specific location for each of these coal mines located in Shanxi, their name and their production capacity. And the dots, the size of the dots indicate the capacity of the coal mine. So in the final last subplot, we have the distribution of bootstrap simulated provincial average emission factors. So these are for, you could think of this as for coal mines of low gas in Shanxi province. So these are going to have a, for example, these might have a average emission factor of around 2.8 and then have this uncertainty as indicated here. So this will work for each of these provinces shown here. Yeah, I guess this is all I have for now.
Thank you, Bubing. This is excellent. Now I'm going to turn over to my colleague Nina Kana, who will moderate our expert discussion panel.
Great. Thank you so much, Zhang. Good evening and good morning to all of our participants. I am Nina Kana, a policy researcher at Lawrence Berkeley National Lab based in Berkeley, California, and I'll be serving as the moderator for today's discussion. So throughout this segment of our webinar, if you would like to ask a question for one of our panelists, please type your question into the Q&A function at the lower bottom right of the Zoom screen. And we will do our best to answer as many questions as we can towards the end of the webinar session. And so I think with that, I will first introduce, I have the pleasure to introduce our three distinguished panelists, followed by about 5 minutes of remarks from each panelist, and then we'll end with the Q&A session. So first, we'll hear from Professor Qin Kai from the China University of Mining and Technology. His research interests are remote sensing of aerosol and trace gases, estimation of CO2 and methane emissions. And prior to joining CUMT, he was a visiting scientist with the German Aerospace Center and also a visiting professor with Yonsei University. Second, we will hear from Professor Zhang Yongguang from Nanjing University. Professor Zhang received his bachelor's from Jilin University and master's and PhD from Beijing Normal University. His primary research areas include the global carbon cycle and hyperspectral greenhouse gas remote sensing, and he has published over 100 peer-reviewed journal articles. And then last, but definitely not least, we'll hear from Dr. Riley Duran, the founder and CEO for Carbon Mapper. Previously, Dr. Duran spent 27 years at NASA's Jet Propulsion Laboratory, including serving as a laboratory fellow and the chief systems engineer for JPL's Earth Science and Technology Directorate from 2008 to 2019, with a broad portfolio of satellite mission and aircraft instrument development, research analysis, and applied science spanning the agency's Earth System Science enterprise. So with this very distinguished panel, I'll start with passing the floor to Professor Qin Kai for his remarks.
Okay, thank you. And it's my honor to sign a little job during the past 3 years. We have done in Shanxi province and the other province about the coal mine methane emissions. So I find your job is really very good to understand the under or over estimation about the emission factors from the view of the national scale. But my experience is that we have to think about at least 2 factors. First is the spatial mismatch. Usually you can get the location of the coal mines from the maybe from the I don't know, you collect the data maybe from the published database about the maybe you get the information from the you get the exact locations, or you just get the company names. I don't know what data you get.
I think Bobing has collected those data, and those data are just directly searched from the map, and we are not so sure if the location, the latitude, longitude represent the exact coal mine location or their head company of location. That is not for sure for our case.
Okay. If we want to know the real station, we have to think about the real emitters from the coal mines. Like they don't have only they have the shaft, and also you have the pump station, and they also have the coal washing factories. So they distribute usually is a relative large areas, along with actives, coal mine actives. Maybe here is the main how to say this main areas, but maybe 10 kilometers away from the main areas of the coal. So the sector is there, and you can get a location. Oh, it's here. So I mean, from the satellite review, satellite view, we just match the pixels. We can get not a really how to say that, gradient of the columns. So I think the first one we need to think about the different emitter factories in the whole coal industry, not only the sector, not only the pumping station, not only the washing factory, and also the transport. The transport, they have some storage station over there. They also have some emissions for the methane, and also before they go to the maybe coking factory or go to the power plant, they also have the emissions. So we need to think about this, the whole coal industry chains. The first is this is the first point I'm thinking, and the second one is we need to think about the detailed emission changes because of the maybe some coal mines, they have used the well about the the low gas, high gas, and or the blast gas. They have used some ones, but this usually is not continuously. Maybe in the it depends on the concentrations of the coal mine emissions. So if the concentration is enough, they can open the power plant to use this. But if it's not sufficient, so just stop and open again. So the real station is really very complex. Not only we think about the from the view of area. If we really want to get a detailed mine special emission factors, we need at least know the usually it's stations and states and their change. They especially during the past 1 year because of the government released the places, so many coal mines have accepted the process to use well the high gas emissions. So in the future, if we want to really to get a real emissions from the coal mine special effectors, I think maybe we need to do more works, and I think it's really challenging. But we can do that. We can do that. The first step is very important. Thank you.
Thank you so much, Professor Qingkai, for those very helpful input and questions. Next, we'll turn to Professor Zhang Yongguang from Nanjing University for your remarks, please.
Hi, good evening. Yeah, so very glad to be here. So really nice. I think 1 month ago, Dr. Jiang was presented some result in Nanyang University in September. I remember that. So it's very interesting that we have a really different efficient factor for different provinces. I have such a few questions. So you mentioned that the man is, I'm quite actually curious. The man depth is not a factor, at least it's not an important factor for the for your estimated efficient factor. I'm wondering if any the co-linearity or covariance between the province and the man depths. You know, like in north, the Kuman actually is not that deep, but in the southwest, as you mentioned in Guizhou, you know, because the geological difference between north and south. So that's why. So the province and man depths probably is the same. At least probably they are the similar factors. You know, in the north, the Kuman is open Kuman. You know, in the north, in Inner Mongolia, in the north of Shanxi province, a lot of Kuman is just open. You know, but in the southwest or in other places, they are quite deep the Kuman. So that's one thing. So I'm wondering whether you, even for one province, like in Shanxi, in the north close to Inner Mongolia, and the southwest close to Henan province, there's a few Kuman in Henan province close to Shanxi. So they are actually have the very similar, you know, the characteristics, the Kuman types, some other things. So it's next step, maybe is it possible to not for the province, just for different groups? You have to maybe you can group different areas based on their common types and also the geological locations. Maybe that's easier. Not easier. I mean, much more clear. You know, to estimate the different efficient factors for different common types, not for the province. So it's quite big in China. So even if some, like in Guizhou, the Kuman are just in one small area, but in Shanxi province in the north, but in Mongolia, in the east and in the west, they're quite different. So not only one province, just for different geological, you know, or common types, maybe it's more. That's just my assumption in my head. This is the first question or first comment. The second one, I'm also curious for the ownership. So the private and the national, it seems like there's no difference, you know, for your estimation of efficient factor. But you know, for the national owned Kuman, they are more, at least from my understanding, is more strict for, you know, they put a lot of policies to, at least for the security reason. But for the private owned Kuman, at least 10 years ago, we heard a lot of, you know, some disasters or something most of that are, you know, happening in the private owned Kuman. So I'm not sure. I mean, for the last 5 years, that doesn't make more difference, but in 10 years ago or even longer, so there should be some difference. I mean, the private owned Kuman probably have a little bit more higher efficient factor than the national Kuman. That's I think Professor Qin have some experience. So that's one thing. Maybe you can think about that. The third one, I'm quite we used some satellite measurements in last 5 years from 2019 to 2023. So for the Shanxi province, our estimation for the emission is around 8.93 TB. So it's quite close to your estimation for the 2023. So your estimation, I remember, is 8.97. So it's really, I'm not sure it's coincidence or there's something, you know, it's really interesting. So we use the hyperspectral sensing with find around more than almost 200 big, you know, the plumes in Shanxi province. Then we estimate this is really close to your bottom-up estimates. That's really interesting. So maybe in the future, you mentioned maybe we should combine the satellite. I think some of our colleagues, Professor Chen, Huilin, his students and my students, they are working on that for the Shanxi province to use only the satellite measurement to estimate emission factors for different command. So that's more specific, not only for province. Maybe then we can collaborate together to. I'm not sure for the southwest, for the Guizhou. I could we could check because southwest is really cloudy. It's not too much images over the year, so it's probably also the terrain, the topographic, it's really complicated, not easy to use satellite measurements. But at least for the north part, Inner Mongolia, Shanxi province, and Henan, and Shanxi, even in Xinjiang, it should be easier to use satellite measurements that combine together. Then we can improve the not only province emission factor, but also can go down to the specific locations for each command. That's some of at the moment, some of my thoughts. Maybe later we can discuss it more. Yeah, thanks so much. Yeah.
Great. Thank you so much, Professor Zhang, for those questions and also the suggestions for future research directions. I think after the last panelist's remarks, maybe we can have some time to see if we have answers from our other panelists on some of the questions you raised. And then with that, I'll turn it over to Dr. Riley Duran as our closing panelist before the Q&A session.
Thanks, Nina, and thanks everyone for inviting me to talk. I'm going to show a few slides, mainly to give you a sense of what's possible, and I think what to look forward to with satellite monitoring of coal mine methane emissions. In this talk, I won't, given the time and given where we are in our research, I won't try to present any causal findings other than to point out that Elise Penn from our team is on the call, and she has been working to analyze our data primarily collected with aircraft and satellites over the US and comparing the top-down and bottom-up estimates, is working on a paper now that describes a comparison both at the individual mine level, but also aggregating at basin scale, and some initial inferences on what we can say about emission factors. But just real quickly, Carbon Mapper is a nonprofit organization that's working to deliver localized and actionable methane and CO2 data. We also lead a public-private partnership based in the US, which includes NASA's Jet Propulsion Laboratory, our commercial partner Planet Labs, and others, to deploy a constellation of satellites that can do very high resolution monitoring of methane and carbon dioxide plumes. We just launched our first satellite, Tanager 1, in August. I'll show some examples at the end of this presentation. But our goal is to work with stakeholders, both governments, industry, and others, to translate data into action and to help understand emissions. And we make all of our data publicly available. We use remote sensing to pinpoint point sources using a technique called imaging spectroscopy. And an example of using this is, here's an example of an airborne remote sensing image over coal mines in Western Pennsylvania and West Virginia in the US. And you can see that we've detected in this case 4 coal mine emissions, and then we can zoom in on individual mines. In this case, we're looking at emissions from a deep underground ventilation shaft. And to highlight a couple of things, one is relatively high spatial resolution. In this case, about 3-meter resolution. With the satellites, we do about 30-meter resolution. More importantly, notice the time series. It's important to understand the sample frequency and to account for both detection and non-detection of plumes, because of course, as it has already been said, these emissions can be highly variable and intermittent. And so an important part of any observing strategy is to provide frequent enough sampling to account for that variability to avoid over or underestimation. So this is just an example. Another thing to consider is validation of the emission estimates themselves. We use a combination of techniques, including independent blinded control release testing, where we can compare what the satellite estimates the emissions with the known release rate, in this case, from a natural gas supply tank, something we're doing right now with the Tanager satellite and aircraft in the US. And I think this is one area for collaboration where establishing scientific standards and approaches for assessing data to verify their accuracy is really important if we're going to apply the remote sensing observations to inventories and bottom-up accounting methods. So here is an example of what I meant by our global data portal. We publish all of our methane data. This is a look at our data portal. You can go to the portal to view the data in different formats. You can also use the API to download data with directed searches. We published about 16,000 of these methane plumes globally so far. And here's just a summary. If I filter on coal mine emissions globally, what I'm showing here in the purple circles are just counts or numbers of methane plumes we detected in different regions. The white polygons show where observations have occurred, and you'll notice in the US, it's fairly dense. This is a combination of aircraft surveys, but also observations from NASA's EMIT instrument on the International Space Station. But if you look around the rest of the world, you'll see that there are large gaps in some areas, and has been previously noted in some regions like Guizhou that are cloudy, that there are relatively few observations, whereas in Shanxi, there's more dense observations. Again, this is limited to the NASA's EMIT instrument. We're just starting to commission the Tanager 1 satellite that Carbon Mapper Coalition launched, and so we expect to see this map filled out in more detail starting in 2025 and with higher frequency measurements. But this just gives you a sense of what we've done to date and where the observations are going. And then I'll just close by showing an example of some of the first light imagery from the Tanager 1 satellite. Like I said, we're still commissioning the satellite. It is on track to be fully operational by February of 2025, at which point we'll begin to routinely publish methane data. This is an example of a landfill methane plume in Karachi, Pakistan. But I can say that we're already detecting coal mine methane emissions around the world, including the US, China, Australia, Poland. The last thing I'll say is I've been focusing here primarily on point sources or condensed high emission point sources. We also occasionally see methane emissions from surface coal mines. And just to point out that, coal mine emissions are not just limited to vent shafts, but also the more diffuse area sources. And not all satellites are sensitive to that. We're not terribly sensitive to it, but this is something we're looking at surface mines, not just underground mines, and why we see more emissions from some mines than others. Is it due with the depth of the mine or the gassiness, the gas content? So clearly a lot of work to do together, and we look forward to collaborating with colleagues here on the call. Thank you.
Thank you so much, Dr. Duran. I think you already kind of dropped a few hints at some of the questions I was going to ask regarding, challenges and opportunities for collaboration between top-down and bottom-up modeling. But before we get to those, maybe I'll see if our panelists have any questions they would like to ask. I think we had two from the audience that was answered in the Q&A chat, but of course we welcome additional questions if you have any to be entered in the Q&A chat.
So perhaps, Nina, I can respond to some of the questions and comments provided by our panelists. First of all, thank all of three of you for your very constructive feedback and your openness to collaborate in the future. We do believe that a combination of multi-scale observations are essential to get to the bottom of the true emissions. So thanks, Professor Qingkai. On your question about the location, yes, that's one of the more challenging aspects of data collection. So far, we're only using the reported address provided by the Chinese government, so it's probably not exactly the coal mine shaft location, but we hope it's not too far. And if possible, I would like to work with folks who are interested to better define those location of data, so we have a better identification that we can use to work with remote sensing teams. For our estimates, that's actually not as essential because we're using reported emission data from those coal mines to generate our algorithm to estimate the data. But I think I understand your point about capturing exact location, but also entire production chain of coal mining, not just coal mine shaft. And then in terms utilization of coal mine methane, you made a comment about utilizing for power generation, depending on the concentration of coal mine methane. We totally agree. I think China is probably a world leader in that technology, in both capturing and utilizing coal mine methane. We understand there's multiple pilot projects as ongoing. We'd like to learn more to understand the efficacy and the cost. We have a separate track of work understanding the cost of mitigation by understanding how much you need to invest to capture those. So we'd love to work with you to understand those specific pilot project. I think Professor Zhang offered a very interesting feedback on depth versus province as a proxy, and that's a very good suggestion. I think we'll try to experiment with our data analysis to see whether by doing a more regional grouping, and that we can tease out whether the depth is indeed a factor or not. That's something that we love to try. But thanks for the suggestion. I think it's very, very interesting. On the ownership question, I think it may become less critical as China has consolidated coal industry. So it's all nowadays is all state-owned coal mines. So that's become a lesser of an issue. I think in regard to the mitigation measure each firm adopt, of course, the central government-owned coal mines are more sensitive to government policy signals. So they might take a more mitigation effort in reducing methane emissions. However, the work we're doing here is understand the level emissions, less so on the utilization aspect, which is critical. We only now understand in the national level the overall coal mine methane utilization, and we actually don't have much information by firm, by province. This is another good research topic to understand that what policy signal people respond to, right? Whether I think there's a CCER that's being proposed in China, which at least on paper sounds very attractive, but whether that's the right policy instrument or not is yet to be proven. I mean, we need to actually probably talk to people in the region to understand what's holding them back on those question. We're very pleased to hear that our estimate for Shanxi, at least extremely close, that offers a great promise to work together to even further refine those. So we'd love to follow up on that as well, particularly your colleagues' work on understanding specific mine location estimates. And for Roddy's comment, it's terrific to see the work you're doing. We're really pleased that you have such expanded instruments that can help us understand much larger geographic scale. The observation you picked up there was very interesting to see. That's already showing up, and also the kind of a seasonality, the frequency observation of which are all critical in capturing more accurately the emissions from each locations. And that's something that would love to work with you as well. I hope at least our initial estimates on point sources and their location give a rough estimate that we can use as baseline for further refinement. In addition to coal mines, I think the observation you shared on landfills is very, very illuminating as well. I think there's some areas we love to work with you as well on that. I'm just providing some basic response to the questions and comment by our panelists. I will stop here to see whether other colleagues will be in the GA have other response or not, and we'll also invite questions from our audience as well.
I'll just echo one comment you made about the synergy with other sectors, is that we have done, with Carbon Mapper, we've done far more work with the oil and gas, waste management sectors, particularly landfills. And we have published several papers recently in the US regarding landfill emissions that I think have a lot of similarities with solid waste management in China, as well as I think the coal sector. And in particular, two findings from those studies with the landfills. One is using remote sensing and atmospheric observation to identify areas where process models are not perfectly representing activity at the surface because of complexities in these engineered systems. They're very complex systems. And additionally, identifying process escapes because of either maintenance activities or leaks or malfunctioning equipment. And those two applications have different implications on the necessary accuracy and what's an acceptable level of uncertainty, and also how quickly the data needs to be delivered. So I think there is a lot of room for collaboration and improvement, and so very much look forward to working on those topics.
As for the release concerns for Chinese landfill and waste, like the wastewater. So right at the moment, probably the emission from landfill in China is pretty low. So most of landfill they burnt, or some other cities they just cover it, really make a very strict policy. But so for the wastewater, we did some measurements in the last few months. I think of the country, so more than 100 wastewater plants. So we found there's some really high emissions. So I'm not sure for the Carbon Mapper for the satellite, at least right now for the hyperspectrum for the Gotham 5 or for image, it's not easy to to detect the emission from wastewater. For the Carbon Mapper, I'm not sure it's good to target some wastewater plants to see whether we can detect the emissions from wastewater plants. Generally, that's around 100 kilograms, around 100 kilograms per hour. Some are less emissions, for the wastewater. That would be right now we have all the locations of the country for the wastewater from satellite, images. Then we measured more than 100 emissions from the ground measurement. So I think if with the satellite, if we can detect it from the wastewater, then we can know how. My understanding is that our estimation at the moment from the bottom-up estimation for the wastewater is underestimated. They should be a little bit higher from wastewater, but for landfill probably is overestimated at the moment. Yeah.
Yeah, that's really interesting, and it'd be great to follow up. We do detect for very high emitting wastewater treatment plants, particularly those with anaerobic digesters. We often see concentrated emissions. We see similar high emissions from concentrated animal feeding operations, like swine and dairy farms, from the manure management, wherever you have anaerobic conditions in highly concentrated waste streams. So I think this is a big area of interest, and I think all of those sectors are of interest with us for follow-up.
Yeah.
Nina, are there any other questions from the audience?
Q&A? No, I believe we answered it in the Q&A box.
Yeah, I think we're actually at time. So thanks all our panelists for your great contributions and the many good common feedback, direction for future research, and filling the gaps we still have. So we will follow up with you. Thank you again. This would conclude this webinar.
Thank you for organizing.
Thank you. Thank you for organizing. Thank you.
Okay.
Yeah.
Thank you, everyone.
See you soon.
Thanks,
Bye-bye.
everyone.
Bye bye.
Thank you.
Bye.
Mhm.
Bye.